At this very moment, you are moving through space at over 2 million kilometers per hour. Not because of Earth's rotation, not because of our orbit around the Sun, not even because our galaxy is spinning. You're being pulled by something so massive, so incomprehensibly large, that it's dragging hundreds of thousands of galaxies, including our own, toward a region of space we cannot see. A region that lies beyond the observable edge of our universe. In 2008, scientists analyzing data from the Wilkinson Microwave Anisotropy Probe discovered something that shouldn't exist. Galaxy clusters across a third of the visible sky were moving together in the same direction at speeds that violate our understanding of cosmic expansion. They called this phenomenon dark flow. The implications are staggering. If dark flow is real, it means there's something outside the observable universe influencing everything within it. Something so massive that its gravitational pull reaches across billions of light years. Something that suggests our universe, everything we can see, measure, or detect, might be just one small part of something far, far larger. Today, we journey through evidence that challenges everything we thought we knew about the cosmos, cosmic expansion, and the very boundaries of existence itself. Prepare yourselves. We begin. March 2008. NASA's Goddard Space Flight Center in Maryland. Alexander Kashlinsky, an astrophysicist studying the cosmic microwave background radiation, the afterglow of the Big Bang itself, notices something peculiar in the data. Something that makes him check his calculations 3 times before calling his colleagues. Galaxy clusters aren't behaving the way they should. According to our understanding of cosmology, the universe expanded from the Big Bang in all directions equally. Yes, galaxies have their own individual motions called peculiar velocities, but these should be relatively random, averaging out to follow the general expansion of space itself. Think of raisins in rising bread dough. Each raisin moves away from the others as the dough expands, but they don't all stream in one particular direction. Using a technique called kinematic Sunyaev-Zeldovich analysis, Kashlinsky and his team examined how clusters of galaxies distort the cosmic microwave background as they move through it. It's like watching how a school of fish creates ripples in water. The pattern of disturbance reveals the direction and speed of movement. What they found defied explanation. Over 700 galaxy clusters across more than 1 billion light-years were moving coherently in the same direction toward a region of sky in the constellation Centaurus. The speed, approximately 1,000 kilometers per second. To put this in perspective, that's over 2 million miles per hour above and beyond the cosmic expansion. This isn't a gentle drift. This is a torrent. Kashlinsky called it dark flow, dark because whatever is causing it cannot be seen within our observable universe. Flow because of its relentless, unified motion. To understand why this discovery sent shockwaves through the cosmological community, you need to grasp what the observable universe actually is. When we look out into space, we're looking back in time. Light travels at a finite speed, 300,000 kilometers per second. The farther away something is, the longer its light takes to reach us. The most distant objects we could possibly see are about 13.8 billion light-years away, because that's how long ago the Big Bang occurred. This creates a cosmic horizon, a boundary beyond which light hasn't had time to reach us yet. Here's the crucial point. According to standard cosmology, nothing beyond this horizon should influence anything within it. The cosmic microwave background radiation represents the surface of this horizon, a shell of ancient light surrounding us from all directions. It should be essentially uniform, and it is, to within 1 part in 100,000. But dark flow suggests something massive enough to gravitationally influence hundreds of thousands of galaxies lies beyond this horizon, pulling them in a coordinated direction. It's as if we discovered that the ocean we thought was calm actually has a powerful current, and we can't see what's creating it. The immediate response from the scientific community was skepticism. Maybe the cosmic microwave background itself had irregularities that created the illusion of flow. Could local gravitational effects from superclusters within our observable universe account for the motion? Kashlinsky's team went back to work. They analyzed different datasets. They checked for instrumental errors. They accounted for every known source of systematic bias. The dark flow remained. In 2010, they published follow-up research extending the analysis to even more distant galaxy clusters, some over 4 billion light-years away. These distant clusters showed the same coordinated motion. The flow wasn't local. It spanned scales that shouldn't show any unified motion according to standard cosmological models. But here's where it gets genuinely strange. The dark flow appeared to be constant across cosmological time. Galaxy clusters that we see as they were, billions of years ago, show the same flow as clusters that are relatively nearby. This suggests that whatever is pulling them has been doing so for most of cosmic history. But the evidence forces us to confront an uncomfortable possibility. What if the universe we can see, all the galaxies, all the stars, everything our telescopes to detect, represents just a tiny fraction of what actually exists? What if something enormous lies just beyond our cosmic horizon, something so massive it's been pulling us toward it since shortly after the Big Bang? The accumulating evidence would prove even stranger than anyone imagined. To understand what might cause dark flow, we first need to understand the structure of the universe itself. The cosmos isn't uniformly distributed. Galaxies cluster together through gravity, forming groups, clusters, and superclusters. These structures create a cosmic web, filaments of galaxies separated by vast voids containing almost nothing. The largest structures we've identified include the Sloan Great Wall, a galactic filament over 1.3 billion light-years long, and the Hercules Corona Borealis Great Wall, possibly 10 billion light-years across. The Big Bang occurred 13.8 billion years ago, and the speed of light limits how far gravity's influence can spread. There simply hasn't been enough time for anything larger to form through gravitational collapse, or so we thought. In 2009, researchers analyzing the Chandra X-ray Observatory data discovered something unexpected. They found that the bulk flow of galaxy clusters extended far deeper into space than previous measurements suggested, out to distances of 900 million light-years. This is significant because at such distances, the standard model of cosmology predicts that individual motions should become increasingly random, averaging out to follow only the cosmic expansion. Instead, the coordinated motion persisted. Scientists discovered more patterns in the cosmic microwave background itself. While generally uniform, there's a subtle asymmetry. One hemisphere of the sky shows slightly different temperature fluctuations than the other. This asymmetry, known as the dipole pattern, aligns closely with the direction of the dark flow. Coincidence? Perhaps. But the probability of random chance was dropping with each new observation. Then came data from the Atacama Cosmology Telescope in Chile. In 2012, researchers used kinematic measurements to track the motion of thousands of galaxy clusters. They confirmed that massive structures were indeed flowing in a preferred direction at velocities inconsistent with standard predictions. The equivalent scale: imagine standing on Earth and somehow feeling the gravitational influence of an object not just beyond Pluto, not just beyond the nearest stars, but beyond the visible boundary of space itself. The mass required to create such an effect staggers the imagination. Conservative estimates suggest that to produce the observed dark flow, the attracting mass would need to be equivalent to tens of thousands of galaxy clusters containing trillions upon trillions of stars concentrated in a region beyond our cosmic horizon. But what could possibly create such a concentration of mass? Several theoretical candidates emerged. First, a pre-inflationary remnant. In the first fraction of a second after the Big Bang, the universe underwent cosmic inflation and exponential expansion that stretched space itself. What if inflation wasn't quite uniform? Such a structure could still exert gravitational influence despite being invisible to us. Second, inhomogeneities in the universe at the largest scales. Our cosmological models assume the universe is homogeneous, the same in all directions at the largest scales. But what if this assumption is wrong? What if there are density variations larger than we could observe, creating gravitational gradients that pull matter in preferred directions? Third, and this is where it gets truly mind-bending, what if our universe is just one bubble in an infinite multiverse, and the dark flow represents gravitational attraction toward another universe? But this represents just one piece of a much larger puzzle hidden in the structure of space-time itself. In 2013, the Planck satellite, the most sensitive instrument ever built to study the cosmic microwave background, released its first full sky map. Scientists around the world scrutinized the data, looking for anything unusual. They found it. The same asymmetry that aligned with dark flow appeared in the Planck data, but with additional unexpected features. There were cold spots, regions where the temperature of the background radiation was lower than could be easily explained. One particularly large cold spot, spanning 1.8 billion light-years across, seemed to align with the general direction of the dark flow. Could this be connected? Some researchers propose that the cold spot represents a supervoidal region containing far less matter than average, through which the cosmic microwave background radiation passes. As light crosses such a void, it experiences a slight energy loss, appearing cooler. But the cold spot seemed too cold, too large to fit comfortably within standard models. Others suggested something far stranger. The cold spot might represent a collision between our universe and another during the inflation era, leaving a bruise in the fabric of space-time itself. The most remarkable discovery involves what's called the Great Attractor. In the 1970s, astronomers discovered that our Milky Way galaxy, along with the entire local group of galaxies, was moving toward a massive concentration of matter located about 220 million light-years away, in the direction of the constellation Hydra Centaurus. This region contains enormous galaxy clusters with a combined mass of tens of thousands of galaxies. For decades, the Great Attractor was considered the source of our peculiar motion, the reason we're moving the way we are through space. But here's the problem. The Great Attractor lies in the same general direction as the dark flow, but it's far too close to account for the vast bulk flow of distant galaxy clusters. When researchers carefully calculated the gravitational pull of the Great Attractor and all surrounding superclusters within the observable universe, they found these could only account for about 44% of the observed motion. Something else was pulling, something beyond. In 2016, researchers identified an even more massive structure they named the Shapley Attractor, a concentration of galaxy clusters seen larger than the Great Attractor, located 650 million light-years away. Combined with other known superclusters, could these account for the dark flow? The calculations suggested no. Even when including every known massive structure, the expected bulk flow velocity was only about 600 kilometers per second, well short of the 1,000 kilometers per second observed in the dark flow data. Research from Australia's Parkes Radio Telescope revealed that the polarization patterns in radio waves from distant galaxies also showed alignment with the dark flow direction. Light waves have an orientation as they travel through space, their polarization. When light passes through gravitational fields or regions of varying density, this polarization rotates. The fact that radio polarization showed patterns aligning with dark flow suggested that whatever's causing the flow affects not just the motion of matter, but the structure of space-time itself, between us and those distant sources. Recent observations from the Very Large Array in New Mexico detected something even more puzzling. The dark flow appears to correlate with the distribution of dark energy, the mysterious force causing the universe's expansion to accelerate. Standard cosmological models assume dark energy is uniformly distributed throughout space, but what if it isn't? What if there are variations in dark energy density at scales larger than we could observe? Such variations could create pressure gradients that push matter in preferred directions, complementing the gravitational pull from beyond the horizon. The evidence extends beyond simple motion into the realm of cosmic structure, the nature of the Big Bang, and the very geometry of existence. The standard model of cosmology called Lambda CDM has been extraordinarily successful at explaining most cosmic observations. It describes a universe that emerged from the Big Bang 13.8 billion years ago, underwent rapid inflation in its first fraction of a second, and has been expanding ever since, with that expansion now accelerating due to dark energy. This model predicts a universe that is homogeneous and isotropic, the same in all directions and at all locations when averaged over large enough scales. Any bulk flows of matter should diminish rapidly at distances beyond a few 100 million light-years. Dark flow violates this prediction. Dr. Kashlinsky and his colleagues proposed that dark flow represents evidence of pre-inflationary physics cosmic structure that existed before the inflationary epoch and got stretched beyond our cosmic horizon during inflation. This structure continues to exert gravitational influence from beyond what we can see. Think of it this way. Imagine inflating a balloon with dots painted on it. As you blow, the dots spread apart, and if you inflate it enough, some dots disappear beyond the edge of the visible balloon surface. But they still exist, and if they were massive enough, you might detect their gravitational pull even though you can't see them. Dr. Laura Mersini-Houghton from the University of North Carolina proposed an even more radical explanation: quantum entanglement on cosmic scales. In quantum mechanics, particles can become entangled connected in such a way that the state of one instantly affects the state of another, regardless of distance. Mersini-Houghton's theory suggests that our universe became entangled with neighboring universes during the inflation era. The dark flow would then represent a quantum correlation between matter in our universe and matter in adjacent universes, with the bulk motion arising from this entanglement. This might sound like science fiction, but quantum entanglement is well-established physics at small scales. The question is whether it'd persist and produce observable effects at cosmological scales. Critics point to systematic uncertainties in the measurements. The kinematic Sunyaev-Zeldovich effect is subtle, requiring careful calibration and analysis. Some research teams, analyzing Planck data with different techniques, found no significant evidence for bulk flows extending beyond 600 million light-years. In 2013, a team from the Institute of Astronomy in Cambridge published analysis suggesting that the dark flow signal might be an artifact of how the data was processed, a result of not fully accounting for the motion of our own galaxy and local group through space. This forces us to reconsider fundamental assumptions about measurement and certainty in cosmology. Are we truly detecting a vast cosmic current, or are we seeing patterns that our minds and methods impose on random noise? The debate continues, with research groups around the world analyzing newer, more precise data. The James Webb Space Telescope, launched in 2021, is now providing the most detailed views of the distant universe ever obtained. While its primary mission involves studying galaxy formation and exoplanets, JWST's data offers new opportunities to test the dark flow hypothesis. If dark flow is real, JWST should detect its signature in the motion of galaxies as they appeared over 10 billion years ago. Early results are intriguing. JWST has revealed that the early universe was more structured than expected, with massive galaxies forming earlier than cosmological models predicted. Whether this connects to dark flow remains unclear, but it suggests our models of cosmic evolution may need revision. The upcoming Euclid mission and the Vera Rubin Observatory's Legacy Survey of Space and Time will map billions of galaxies across the entire visible sky. These surveys will measure galaxy positions, shapes, and velocities with exquisite precision, providing the statistical power needed to definitively confirm or refute bulk flows at the largest scales. Within the next decade, we'll have our answer. Recent breakthroughs suggest another approach: gravitational wave astronomy. The LIGO and Virgo detectors have opened a new window on the universe by detecting ripples in space-time from colliding black holes and neutron stars. Here's the key insight. If there are massive structures beyond our cosmic horizon, they might produce gravitational waves that propagate into our observable universe. These waves would carry information about whatever lies beyond a message from the unseeable. What would it need if dark flow is definitively confirmed? First, it would require revising our cosmological models. The assumption of homogeneity that the universe is the same everywhere at large scales would need to be abandoned or modified. The universe would be revealed as far more structured and complex than current models suggest. Second, it would provide evidence that our observable universe is indeed just a small part of something larger. The cosmic horizon that marks the edge of what we see would be recognized as merely a limit of observation, not a boundary of existence. Are there structures perhaps formed before cosmic inflation that dwarf anything we can imagine? Could there be intelligence or civilizations in those unreachable realms, experiencing entirely different cosmic environments? The philosophical implications are equally profound. For centuries, humanity has grappled with our place in the cosmos. We learned that Earth isn't the center of the solar system, the Sun isn't the center of the galaxy, and our galaxy is just one of hundreds of billion. Dark flow suggests we must take another step in that cosmic humbling. The entire observable universe, every star, galaxy, and structure we can possibly detect, might be just a local neighborhood in something incomprehensibly vaster. This forces us to reconsider fundamental assumptions about cosmology, physics, and the nature of existence itself. If something beyond our cosmic horizon is pulling hundreds of thousands of galaxies, what else might be out there? Some theoretical physicists propose that our universe is just one bubble in an eternally inflating multiverse. In this model, inflation never completely stopped. It continues in most of space-time, but occasionally forms pockets where inflation ends and a bubble universe forms. Each bubble might have different physical constants, different strengths of fundamental forces, different masses for particles, perhaps even different numbers of dimensions. The vast majority would be inhospitable to life, but among infinite bubbles, every possibility would be realized somewhere. Dark flow, in this context, might represent gravitational attraction toward other bubble universes that happen to form near ours in the eternally inflating multiverse. We're being pulled toward neighbors we can never reach, separated by expanding regions of inflationary spacetime. The most profound implications emerge when we consider the nature of cosmic horizons themselves. Our observable universe has a radius of about 46 billion light-years larger than the 13.8 billion-year age of the universe might suggest, because space itself has been expanding. Anything beyond this horizon is causally disconnected from us. No signal from there can ever reach us, because the expansion of space carries it away faster than light could travel. But here's a disturbing possibility. What if our cosmic horizon isn't a special boundary? What if observers in distant galaxies, now beyond our horizon, also have horizons and they overlap? The universe might be an infinite patchwork of overlapping observable regions, each containing observers who can never contact each other, yet all connected by gravity's infinite reach. In such a universe, there would be no privileged center, no ultimate reference frame. Everything would be equally valid as a center of observation, yet fundamentally incomplete in its view of reality. Recent theoretical work suggests just stranger possibilities. Some models propose that space itself might have defects, cosmic strings, or domain walls left over from phase transitions in the early universe. These defects could extend beyond our cosmic horizon, creating gravitational effects that reach across the observable universe. A cosmic string, despite being thinner than an atomic nucleus, would contain as much mass per meter as a mountain range. A string extending from within our observable universe out beyond the horizon could create exactly the kind of directional gravitational pull observed in dark flow. Perhaps the most unsettling interpretation comes from modified gravity theories. What if gravity doesn't behave the way Einstein's general relativity predicts at the very largest scales? What if there are additional forces or modifications to space-time curvature that only become significant across distances of billions of light-years? Such modifications could potentially explain dark flow without requiring anything beyond the observable universe. But they would mean that our fundamental understanding of gravity, tested precisely within our solar system and around black holes, breaks down at cosmic scales. This would be both a crisis and an opportunity. A crisis because it would mean our most successful theory of gravity is incomplete, but an opportunity because it would open the door to new physics, new understanding, new possibilities. The ultimate question remains: is the universe we observe truly all there is, or merely a tiny island in an ocean we're only beginning to glimpse? What we've discovered is that this observation opens profound questions about the nature and extent of reality itself. Whether dark flow proves to be real or an artifact of measurement, the questions it raises will shape cosmology for decades to come. If confirmed, dark flow tells us that the universe is far larger and more structured than our cosmic horizon reveals. It suggests we live in a local region of something vaster, pulled by forces originating beyond what we had ever observed. It hints at pre-inflationary structures, quantum entanglement across cosmic scales, or even neighboring universes in an infinite multiverse. If refuted, the story becomes equally fascinating. It would demonstrate the challenges of measuring cosmic-scale phenomena, the importance of systematic uncertainty, and the need for ever more precise observations. It would remind us that the universe does not easily give up its secrets. The current scientific consensus remains divided. Some researchers are convinced that dark flow represents a genuine cosmic current, while others maintain that more mundane explanations or systematic errors account for the observations. But regardless of the final verdict, the dark flow hypothesis has already succeeded in its most important function. It has pushed us to question our assumptions, to improve our methods, and to imagine possibilities beyond our current understanding. We are creatures bound to a small planet, orbiting an ordinary star, in one galaxy among hundreds of billions. Yet we possess the ability to ask questions about the universe at its very largest scales. We can detect and analyze light from galaxies billions of light years away. We can infer the presence of structures we cannot see through their gravitational influence, and we can wonder what lies beyond the horizon. The universe is vast beyond human comprehension. The mysteries embedded in its structure may never be fully resolved. But the journey of discovery, the process of questioning, observing, analyzing, and understanding defines us as a species. Somewhere beyond the edge of everything we can see, beyond the furthest reaches of cosmic light, something may indeed be pulling us forward. The universe is vast. The mysteries are endless. The journey continues.